All right, so in this set of notes, we are going to be talking about integrating integrals whose antiderivative would be the inverse trigonometric functions, integrating general exponentials, and integrating functions whose antiderivative would be the natural log. So in order to figure out the integrals where the inverse trigs would be their antiderivatives, we need to think the other way around. So remember, if you integrate the derivative of a function, you should get the main function out. So remember, we kind of double check integration by taking the derivative of that antiderivative, and we should get the integrand. So what I'm going to do is I'm going to request that if you're watching this video for the first time, you go ahead and write down all of the derivatives of the inverse trig functions as the integrands. If you need to look back in your notes, or if you need to look inverse trig derivatives up online, you can go ahead and do that. But I want to see if you can write this up properly. Otherwise, I'm going to put them up on the screen right now. There we go. So we kind of have these. I have them roughly in the same order. First two go in the first row, second two go in the second row, last two go in the third row. I'll just write that up really quick. 1 over the square root of 1 minus x squared. Don't forget the differential is sine inverse of x plus c. Cosine inverse, that'll just be the same as sine inverse's integrand, except negative. Secant inverse, that's derivative is 1 over the absolute value of x times the square root. And the way that I remember this is if I had to write that absolute value of x first, then I'm going to start on the inside of the square root with the x squared and then minus 1. Cosecant's derivative is going to be the same as secant inverse, except negative. And then tangent inverse, no square root in this one. 1 over, and I don't care if you put 1 plus x squared or if you put x squared plus 1. The addition doesn't matter here. Cotangent inverse's derivative is the same except negative. Now I will tell you, because it can be obnoxious to memorize 6 different integrals, I suggest just memorizing the positive ones. And in fact, let's say I did get a negative integrand, then my antiderivative would be negative sine inverse. I don't necessarily need to remember that it's going to be cosine inverse. It's just kind of up to you if you want to memorize all 6, or if you'd rather just say, hey, I'm going to get negative sine inverse instead and just call it a day. I will have all answers available, but personally, I'd prefer just to memorize my positive ones. And if I remember that it would be the opposite inverse trig function, then that's fine as well. And I'll show you a situation today where it could be one or the other. It's just kind of up to you. So I'm highlighting the boxes that I prefer to memorize. Let's take a look at example 1. Okay, so personally, I think that this example kind of sort of looks like the inverse trig derivative. Again, kind of. I think I'm personally going to need to do a little bit of algebraic manipulation, some u substitution, and I should get it to resemble this except with a u. I'm going to write myself a little note. Looks kind of like tangent inverse derivative. Let's try some algebraic manipulation and u subs. All right, so by algebraic manipulation, what I would like to do in order to make this look more like that tangent inverse derivative is I absolutely need that constant to be a 1. So I'm going to try factoring out a 9 from the denominator. If you notice that any of these could potentially be manipulated to look a little bit more like the inverse trig derivative, always try to factor it out so that that constant becomes a 1. You could do u subs for your variables, but you need that other number to be a 1. All right, so if I factor a 9 out of that denominator, I'm going to be left with 1 plus 16 over 9 x squared. And I moved that differential, the dx, to after the fraction. I just prefer to not have it in the numerator. But if you like having it in the numerator, that's perfectly fine. I'm going to rearrange this one more time so that one, I'm moving that 1/9 in front of the integral since it's just a coefficient. And I'm also going to rearrange the denominator so that I have some expression squared where the x is. So I should have 1 plus 16 over 9 x squared left, but I'd like to rearrange it so that I have an expression squared instead of just my x. And I noticed that 4 squared is 16 and 3 squared is 9. So I'm going to rewrite that as 4 over 3x and that entire quantity squared. Now, if you didn't have a very nice perfect square as a coefficient, you could just say, like, let's say that this was 15. That is way too big. Better. So if I had like a 15 over 9, I could say square root 15 over 3, and that would be okay. But this makes it easier for me to say, oh, hey, look, if I let u equal that expression being squared, this is going to look exactly like the tan inverse derivative. So let's get into the u sub. Let's let u equal 4 over 3x. Take the derivative. We get 4 over 3. And then I'm going to have to rearrange the derivative. I don't have the 4/3 outside of where I'm replacing the u. So I'm just going to solve for dx only. Multiply the dx to the other side. And then multiply by the reciprocal to get the 4/3 to the other side. All right, let's go ahead and substitute. dx gets replaced with 3/4 u, or I'm sorry, 3/4 du. And then I can technically take that 3/4 and move it again as a coefficient in front of the integral, since it's just a coefficient being multiplied by the integrand. I'm just going to reduce that right now. 3/4 times 1/9 is 1/3 times 1/4, or 1/12. Antiderivative of that integrand, tangent inverse, or I could say negative cotangent inverse. It's technically negative cotangent inverse would then be positive in the integrand. Keep it general. And then we can go ahead and sub the u back in. All right. Let's look at the next problem. Okay, we have essentially 1 over x times the square root of 4x squared minus 1. This somewhat looks like the, which inverse trig derivative? Secant inverse or cosecant inverse. So again, I'm going to try doing some algebraic manipulation, some u substitution. And I will say, since we have that plane 1, I don't have to factor anything out. It's literally just going to be figuring out what the u sub needs to be. So like I said, we don't need to do any algebraic manipulation. We have a plane 1 already. So we just need to figure out a good u sub here. If I factor that x, or if I not factor, if I rearrange that first term to be 2x and that entire quantity squared, then I would have a good u sub there. Let u equal 2x and du over dx equals 2. I don't have, outside of where I'm replacing that u, I don't have a 2 anywhere else. So I'm going to straight up solve for dx. So we get du over 2 equals dx. Let's do some replacement. Hold on. Dx gets replaced with du over 2. But I still have that x left over. Do you remember what we can do in order to get rid of that x? We should solve our u equation for x and replace it with something that has a u inside of it. So if I solve that u equation for x, I would get u over 2. And now we only have u's in our equation. There is one thing I'm going to do to simplify. Technically, I can cancel those 2's out because within the denominator, I have a 2 that's kind of like in a numerator and a 2 that's kind of in a denominator. Or if we were to simplify, we would definitely have a u or a 2 completely canceling out regardless. So I can cancel those out right here without having to do too much extra work. And that does look exactly like the secant inverse integrand or secant inverse derivative. So integrating this, the antiderivative is secant inverse of u plus c, or technically negative cosecant inverse of u plus c. And then go ahead and back substitute. Okay, let's try the next one. And this might seem weird, that's the antiderivative, but I guarantee you, because of all of those weird x's, that would actually be the derivative that we see in the integrand. And you could even try it. I think doing that sometimes is really worth kind of seeing how it all plays out. All right, and then this last one. I feel like this is a pretty big stretch, but because I have the square root of 1 minus something that has a square in it, I want to say this very loosely looks like the sine inverse derivative. Now I could be completely wrong. In the sine inverse derivative, I should have a plane 1 in the numerator, but it doesn't hurt to try to do a u substitution and see if it works out. If it doesn't, so what? You wasted like 5 minutes. You could always try it again with something else. It's better to try a strategy than to just sit there blank and not know what to do for like 10 minutes or longer. One thing that I will do really quick to rearrange this is I'm going to rewrite that denominator as 1 minus 5 to the x squared. Remember, power to a power, you multiply those powers. Plus it makes it so that I can do a u substitution and know what's actually getting squared. We'll let u equal 5 to the power of x. And let's see if we remember how to do the derivative of a general exponential. We reviewed it a few times. It should be ln of 5 times 5 to the power of x. Or you can put the ln of 5 after. Doesn't matter to me. Now, because I do actually have the 5x in my integrand, I'm going to leave the 5x on the right side, but I'm going to divide the ln of 5 to the left side with the du. Which means I can replace that with the du over ln of 5. And then we have square root of 1 minus u squared. Okay, with the exception of the ln of 5, this does definitely look exactly like the sine inverse derivative. Luckily, ln of 5 is just a coefficient, so I can go ahead and factor that in front of the integrand. And we get 1 over ln of 5 times sine inverse of u plus c. And remember, you could also write negative cosine inverse of u, and that would be okay. All right. Make sure that if you do have any questions, you're writing them down and asking them during class. Let's go ahead and take a look at the last half of the notes. Exponential and logarithmic antiderivatives. Okay. So just a little reminder from the very front of the notes. Hold on one second, let me try to move this. There we go. When we integrate a derivative, we get the normal function out. Or when I take the derivative of the antiderivative, I get the integrand. So I am going to just kind of remind us about the derivative of the general exponential. When we take the derivative of the general exponential, what do we get out? In this case, it would be b to the x times ln of b, ln of that base. So just like I have written in that top right corner, if I integrate that derivative, integral and the, well, d dx essentially cancel each other out. And excuse my lack of proper notation here. I end up getting a situation like this. Well, if I just want to know what the integral of b to the x is, not integral of b to the x ln of b, I could divide that ln of b to the other side, again, because it is just a coefficient. So the antiderivative of the general exponential is b to the x over ln of b plus c. And then on the other side, we already know the antiderivative of 1 over x, or any of those variations that we see up there. That would be ln of the absolute value of x plus c. All right, so let's go ahead and get into example 2. So in part A of example 2, we are given a general exponential that's getting divided by 6. The division by 6 is literally just a coefficient, so that's fine. In order to integrate this, I'm going to have to do a u sub, so I only have a plain variable in the exponent. We'll let u equal 2x minus 4. And du dx would be 2. Because I don't have just a plain 2 in my integrand here, I'm going to solve for dx completely. So I would get du over 2 equals dx. All right, let's go ahead and u sub. So that would be 7 to the u over 6. And then dx gets replaced with du over 2. I am going to go ahead and factor out the coefficient. Technically, that would end up being 1/12. And then we will actually integrate 7 to the power of u du. As we just saw, the antiderivative of the general exponential is the same function, but it's divided by ln of its base. Keep it general. Let's go ahead and back substitute. So that would be 7 to the 2x minus 4 over 12 ln of 7 plus c. All right, let's do one more exponential one, and then we'll get on to the logarithmic ones. Here I know that I have a general exponential because I have a number as a base and then a function as the exponent. I'm going to try to replace the function that I have as an exponent with u. That way I have just a plain variable up there. And the derivative of sine is cosine. I do actually have cosine in my integrand, so I will leave that on the right-hand side. Okay, so I'm going to go ahead and replace cosine theta d theta with du, and then I will replace the sine with u. I know that antiderivative would be 10 to the u divided by the, or ln of 10. Keep it general, and then back substitute. All right, last two problems. So part C, hopefully this looks like it would be some version of, I guess, the logarithmic antiderivatives integrand, because we just have some linear function in the denominator. So it's not just a plain x, but it is close enough to just having a plain x down there. So I am going to replace the denominator with a u. And generally, we try to do that with u substitutions. If it doesn't look like any of those inverse trig derivatives, we generally want to replace some sort of the denominator with u, so that we either get the natural log as the antiderivative, or something cancels out somewhere else and maybe we get like a power function instead. But otherwise, since we don't have a quotient rule for integration, replacing the denominator with a single variable is super helpful. We don't have a 4 that we're not replacing, so I'm just going to completely solve for dx, which means dividing the 4 to the other side. All right, so over here, that 4x minus 7 gets replaced with a u, and then the dx gets replaced with du over 4. I'm going to go ahead and factor that 1/4 out front. And then I know the antiderivative of 1 over u is ln absolute value of u plus c. And then I go to back substitute. Okay. Last problem. As I mentioned before, when we have a quotient as the integrand, typically we want to try to replace either the entire derivative, or if there's like an inside function within the denominator, we want to replace that with a u, because otherwise we don't have a quotient property for integration. Now, because this doesn't look like an inverse trig integrand, I will go ahead and replace the entire denominator. There's no algebraic manipulation I can do to make this look like any of those inverse trig derivatives. All right, so we're going to let u equal x cubed minus 7x plus 9. And the derivative, well, that is 3x squared minus 7. Now, I don't quite have that in my integrand, but I'm noticing that the numerator is double that amount. So if I were to factor a 2 out of the numerator, I could straight up replace that and the differential with du. Okay, so let's go ahead and do that. I have 2 over u, and then that factor in the numerator and the dx gets replaced with du. That 2 is just a coefficient. I'm not going to bother moving it out front. It's fine if you want to leave it inside. The antiderivative would be 2 ln absolute value of u plus c. And then back substitute, and we are finished. Nice job, everybody.